In this presentation, I'll be explaining pulse width modulated or PWM inverters that single and multiple pulse modulation techniques are used for controlling the output voltage, magnitude and frequency. Now let us see pulse width modulated or PWM inverters. PWM pulse width modulation is the most suitable method of voltage control. It not only controls the voltage, that is both magnitude and frequency, but also reduces the harmonic content. And already we have explained the different square wave inverter as well as the bridge inverter with 120-degree conduction as well as 180-degree conduction mode. All these cases, the output voltage magnitude can be changed only by changing the DC input voltage. But in this method, that is pulse width modulation techniques, we can change both magnitude and frequency as well as certain harmonics can be reduced, that is also reduce the harmonic content by using PWM technique. The various PWM techniques are single pulse modulation, multiple pulse modulation, sinusoidal pulse width modulation or sinusoidal pulse modulation. And in this presentation, I'll be explaining single pulse modulation and multiple pulse modulation. The next presentation, I'll be explaining sine pulse width modulation, sine PWM. Therefore, it is used in the voltage source inverter, that is VSI, to control the output voltage, both magnitude and frequency, and the output harmonics. By controlling or by this modulation techniques, we can control the magnitude of voltage as well as frequency of the output inverter voltage, and also the harmonics can be reduced or eliminated. Now let us see the single pulse width modulation. Single pulse modulation, this is the single phase inverter topology. There are two legs. These two legs switches S1 and S2, S3 and S4. These are the control switches. Across each switch there are feedback diodes D1, D2, D3, D4, and this is the load, and this is the DC voltage, input voltage V, and the load is connected between the point A and B. And what we are considering is that positive voltage means here plus with respect to here, that is taken as a positive voltage. Similarly, if the current is in this direction, it is taken as positive current. Therefore, this is a single phase bridge inverter topology, circuit topology. Now, let us see the single pulse modulation technique of these switches. There is only one pulse per half cycle, that is per half cycle. If you take the half cycle 0 to pi, that's a one half cycle. There will be only one pulse will be there. Then from next pi to 2 pi radian, that is the next half cycle, another, or per half cycle only one pulse is there. Now per half cycle, and the width of the pulse is varied to control the inverter output voltage. This width of this pulse can be varied so that the RMS value of the output voltage can be changed. Therefore, here the switching signal, the gating signal to this one, that is the gating signal to the switches S1 and S2, that is the top one. S1 and S2 is the top one. That is, during this period, the gating signals are given to S1 and S2. At that case, here you can see that plus terminal is connected. Here it is minus terminal is connected. Across the load, you are getting a positive voltage, plus here, minus here. Therefore, you are getting a positive voltage, which is same as the DC input voltage V here. Between the point, this duration, that is delta duration, you will be getting a plus V. And using this, there is no output voltage. And next pulse is given to this S3 and S4, the switches S3 and S4. That is, this pulse is given during this period. Again, here the width is equal to delta, so that here when S3 and S4 are conducting, this positive terminal is coming here and the negative terminal is coming here, or the voltage of this point with respect to this equal to negative, or negative minus V is getting, here minus V voltage is getting. Therefore, the voltage across the load equal, that is shown here. This is the voltage across the load. And by controlling the width of this pulse, that is this delta can be controlled, or you can say that delta can be controlled from, say, if delta equals to delta, in between that delta can be more than 0 and the maximum value equal to pi. And if it is pi, it is a square wave inverter, and it can be it is in between 0 and pi. The pulse width can be changed, delta can be changed from 0 to pi, so that the output voltage here can be changed here. And if you calculate the RMS value of this voltage, if you say the RMS voltage, to calculate that one, see this terminal, this is equal to pi by 2. Of course, this is equal to pi. Therefore, this point is equal to pi by 2. Therefore, this is equal to total delta. This side delta minus delta by here. If you see that pi by 2 minus delta by 2, and here it is equal to pi by 2 plus delta by 2. Therefore, this is the, if you calculate the RMS value of here, square root of integrate v squared d omega t, limits are pi by 2 minus delta by 2, pi minus delta by 2 to pi by 2 plus delta by 2, that is this one, pi plus delta divided by 2. And there are such two pulses are there, that is into 2, and that is divided over 2 pi. So it's a root mean square value. Square root of 2 by 2 pi integral pi minus delta by 2 to pi plus delta by 2 v squared d omega t. If you integrate, you will be getting v into root of delta by pi. Therefore, this is the RMS value. This is the total RMS value of this output inverter voltage of this one is given by v into, that is DC voltage, into root of the pulse width delta divided by pi. As a certain case, if you assume that delta equal to pi, that is, as we have seen in a square wave inverter, if this delta is equal to pi. If it is delta equal to pi, substituting here, we can get it is equal to RMS value equal to V. Therefore, by controlling the pulse width, the RMS value of the inverter output voltage can vary from, of course, we can say that it can be vary from 0 to V. Therefore, the parameter that controls the voltage magnitude variation is this, that is delta, so that the RMS value of the output voltage is given by V into root of delta by pi. And of course, the this RMS value of the output voltage, and the frequency can be changed by changing this duration. That is, if, for example, if you want to get a fundamental output frequency equal to 50 Hz, then you have to select 0 to 2 pi as 20 milliseconds. 0 to 2 pi as 20 milliseconds. Therefore, here pi equal to 180. This is 0 to 180. That's equal to 10 milliseconds. By changing this pulse width, of course, you can vary the magnitude, but almost the fundamental we have a frequency of 50. Therefore, by changing this time duration of this time period, you can change the output frequency of the inverter, and by changing the pulse width, you can change the RMS value of the output voltage. Now, continuing single pulse width modulation, Fourier analysis of this output voltage, we are going to do the Fourier analysis of this output voltage. Output voltage, as this waveform has two property. One we call half wave symmetry is there. Half wave symmetry means Ft equal to minus of Ft plus T by 2. Ft equal to F minus of Ft plus T by 2. And odd symmetry also there. Ft equal to minus of F minus T. Therefore, this waveform has got two property like odd symmetry as well as half wave symmetry. In this case, in the Fourier analysis, as you know that Fourier series, the equation for Ft can be written as Fourier splitting of the constant A0 plus sigma n equal to 1 to infinity an cos n omega t plus bn sin omega t, where A0, an, bn are the Fourier constant. In that case, if these properties are there, it is equal to an equal to 0. Similarly, A0 is also 0. Only is bn will be appearing. That too, we see that bn is equal to the constant Fourier constant bn is can be calculated as, that is, here it is calculated 8 by 2 pi, because we are calculating of this one, and then that's multiplying by 1 here, 8 by 2 pi integrate this limit. You have to see what is this limit, that is here pi by 2 minus delta by 2, pi by 2 minus delta by 2. The upper limit is pi by 2 plus delta, this upper limit is here the upper limit we are taking this point because we are taking only the half of that one, and that is because of this odd symmetry as well as half word symmetry, that is multiplied by 8 by 2 pi here. Therefore 8 by 2 pi integral minus pi by 2 minus delta by 2 this point up to this pi v sin omega t d omega t. Now if you, it is equal to 8v by 2 pi, 8v by 2 pi, that is minus cos omega t. Therefore, when you substitute it is, you can interchange the limits. Cos, that is here pi minus delta, cos n into n omega t is actually cos n omega t. Cos n pi minus delta by 2 divided by n, or that's equal to 4v by n pi sin n delta by 2. Sin delta by 2. That is, this is the Fourier constant Bn, 4v by n pi sin n delta by 2. Or here output voltage V0 equal to sigma, that is, this is present only when n equal to 1, 3, 5, 7, etc. Odd harmonics will be present. Therefore, sigma n equal to 1, 3, 5, etc. Bn, 4v by n pi, this is a Bn sin n delta by 2, this is a Bn, that into sin omega t. Therefore, the fundamental quantity of this one can be obtained by substituting n equal to 1, which is equal to 4v by pi sin delta by 2 sin omega t. Therefore, when n equal to n, it is equal to 4v by pi sin delta by 2 sin omega t. Or this is the maximum magnitude of this fundamental, and once you get the maximum magnitude, you can calculate what is the RMS value of the fundamental, which is equal to divided by root 2, or you'll be getting 0.9v sin delta by 2. This is the RMS value of the fundamental, 0.9, whatever the DC voltage, into sin delta by 2. Delta is the pulse width. Therefore, by changing this delta, we can vary the RMS value of the fundamental. For the inverter output voltage, fundamental RMS value can be changed by changing this duration delta. For example, similarly, the magnitude can be changed. At the same time, certain harmonics can also be eliminated. Certain harmonics can be eliminated by controlling the pulse width delta. As an example, when delta equal to 120 degree, if this pulse width equal to 120 degree, third harmonics will be eliminated. Third harmonics will be eliminated. You can substitute in this one. When it is in delta equal to 120 here, this quantity, that is sin n delta, sin n delta by 2 divided by 2 sin t, or that corresponding magnitude will become, Bn will become 0. Or when the pulse width equal to 120 degree, if you substitute in this one, this of course the Bn here, this is the Bn. If you fifth harmonics, the 120 degree here, sin third harmonic, sin 3 into delta equal to 120. 120 divided by 2 means 60. 3 into 60, sin 360. Sin 3 into 120 by 2. Sin 3 into 60. That's equal to sin 180. This quantity, this Bn will become 0. Therefore, for third, if we are keeping the pulse width to 120 degree here, third harmonic will be absent. Therefore, by another example, if you select delta equal to 72 degree, if this pulse width equal to 72 degree, substituting here in this equation, the fifth harmonics will be, because 5 into 72 divided by 2, that is again, it is equal to, sin, that is sin 5 into 72 divided by 2. That this will become 0. Sin 180, that become 0. Therefore, fifth harmonic will be absent when delta equal to 72. That is why by selecting proper value of this delta, certain harmonics can be eliminated in this one. Another thing is that by controlling the value of this delta, the RMS value of the output voltage or RMS value of the fundamental output voltage can be changed. Now let us multiple pulse width modulation. That is multiple pulse modulation, square wave PWM. Again, this is also called square wave PWM. In this one, this is a circuit topology same as I already explained. S1, S2, S3, S4, feedback diodes D1, D2, D3, D4, The load is connected between the terminals A and B. This is taken as a positive voltage with P plus with respect to here, and this is a positive current, and this is the DC voltage. That of course. Now here in this one, the switching method is like this one. During the S1 is on during the entire positive cycle. Whenever you want to get a positive output voltage, during that entire period, S1 is closed. And S2 is switched on and off. S1 is closed during the entire positive voltage for cycle. And here S2 is being controlled. When S1 is closed and S2 is controlled here, when S2 is on, here you are getting a positive voltage. When S2 is off, you will be getting a zero voltage. That is why that is like this one will be getting. The output voltage will become this one. That can be obtained by controlling two signals, like say this is called the carrier signal, which is a triangular signal, carrier signal, and this is a, of course, this is a square wave. This is also square wave. This is called the reference signal. Square wave is the reference signal, and carrier signal is the triangular signal. We are comparing the reference signal as well as the carrier signal. And during the positive half cycle, that is output, these are during positive half cycle here, S1 is completely closed. And when the reference signal, this is a reference signal, is more than this carrier signal, switching signal is given to S2. When that is during this period, you'll be getting output, that is plus V will be available here. And again during this period, that is VR is less than VR, more will be getting switching. When the reference signal is less than the carrier or the triangular signal, carrier signal, then this is switched off. They will be getting zero voltage. Again during this region, the reference signal is more than the carrier signal or the triangular signal here. BC more than BC, VR is more than BC. Again, you are giving the switching signal to the S2. Then you will be getting plus voltage across the load. That is repeated. Therefore, here looking from to this one, you can see that one. There are three pulses are there in this half cycle. Three pulses are getting in this half cycle. And again in this half cycle, negative half cycle of this one, that is in the negative half cycle, entire negative half cycle, S3 is switched on and S4 is controlled. Previously, positive half cycle, S1 is switched on and S2 you are controlling to control the pulse width. And the negative half cycle, S3 is switched on and S4 is being controlled. When S4 is being controlled, the rule is same thing as we are seeing here. That is, the switch S4 is switched on when the magnitude of reference voltage is more than magnitude of the control voltage. Control voltage means this triangular voltage. Whenever this voltage is more than this magnitude here, then you are switching on this corresponding switch S4. When S4 is on, you'll be getting plus here and minus, or you are getting a negative voltage across the load. You'll be getting negative voltage during this period. Again, when reference voltage is magnitude is less, of course, less than the carrier's BC here, carrier signal, that is switched off. This S4 is switched off. Then you are getting a zero voltage. Again, during this period, the reference signal voltage magnitude is more than the carrier signal VC, then again S4 is on. Therefore, you will be getting a negative voltage here. Therefore, that there are three pulses are getting at the negative half cycle and three pulses are getting at the positive half cycle. And here, by controlling, normally the carrier signal magnitude does not change, but you can change the magnitude of the reference signal so that this level can be either increased or decreased, so that the pulse width of this pulse width can be changed here. And the number of pulses available in the half cycle depends upon the number of cycles of this carrier, or VC number of pulse width, that will be deciding the number of pulses in this each half cycle. Therefore, this is a multiple pulse modulated square wave in which the reference signal, a square wave reference signal, is compared with a triangular signal. And as the reference signal magnitude is more than triangular signal, corresponding switch is on and you will be getting a voltage. And if it is less than, it will be zero. Then you will be getting, that switch is off and you will be getting a zero voltage. Therefore, that is the working of this modulation technique. And in this case, there are two terms are to be defined. That's what is called modulation index, amplitude modulation index, MA. Amplitude modulation index means that it is the ratio of the amplitude of the reference signal, that is this amplitude of the reference signal. This reference signal is the square wave signal, is the reference signal, that magnitude divided by or the amplitude of the amplitude of the carrier signal. The maximum magnitude of the carrier signal is this one. This is the maximum magnitude of the carrier signal. That ratio we call it as amplitude modulation index, MA, or it is equal to the ratio of the, here it is equal to this height or this AR divided by AC. That's called, by controlling MA means that by controlling this height of this one, you can control the amplitude modulation index. Thereby you can control the magnitude of the output voltage. And similarly, frequency modulation is that MF is that it is actually the ratio of the control signal, that is ratio of the control signal to the ratio of the frequency of the control signal, the ratio of the frequency of the control signal to the frequency of the reference signal. That ratio we call it as frequency modulation ratio or for frequency modulation index, MF. Therefore, MF is given by here FC divided by FA, that is frequency of this carrier divided by the frequency of the reference signal, and amplitude modulation index MA is given by the magnitude of this, magnitude of the reference signal divided by the magnitude of the carrier signal. Therefore, MF indicates the number of pulses per cycle. The MF represents the number of cycles per pulses per cycle, that is MF. In this case, we'll be seeing what is the value of the MF corresponding to this case. Now continuing the multiple pulse width modulation, square wave PWM. As I already told you, this is a circuit topology, and this is the reference signal that is compared with a carrier signal. Therefore, as you change the height of the reference signal here, you can change the pulse width. Therefore, this is the output voltage, and the output voltage can be varied by varying the pulse width. Therefore, by changing the pulse width, you can vary the, of course, the RMS value of the voltage, output voltage of the inverter. And variation of delta can be accomplished by rising or lowering the reference signal. Therefore, by varying the height of this reference signal, this width can be changed. Because once the reference voltage is more than the carrier voltage, that is given, you are giving the switching pulse to this one, then you are getting the output voltage. Therefore, by controlling the height of the reference signal, this pulse width can be changed. By changing the pulse width, you can change the magnitude of the output voltage. And here, the number of pulses per half cycle, that is, in this case, the number of pulses per half cycle is equal to 3. Therefore, number of pulses per half cycle is given by what, that is equal to carrier frequency, that is the carrier frequency divided by 2 times, okay, that is 1 by, here this is 1 by 2 FA, that is the FR, that is F0, it is not that. 1 by 2 F0 means the frequency of the reference signal. Therefore, this one, that is FC divided by 2 times F0, that is called that much number of pulses per half cycle. In this case, the number of pulses per half cycle is given by, here it is equal to 3 is the number of pulses per half cycle. Therefore, the number of pulses per half cycle is equal to FC divided by 2 times F0, where FC is the carrier frequency and F0 is the reference signal frequency. Here you can see that when the carrier frequency is 6 times the reference, that is, if you consider one cycle as of the reference signal, there are 6 pulses are there. Therefore, 6 times the reference signal, that is why FC by F0, that will become 6. So 6 by 2, 3. That is why the number of cycles per half, it is equal to 3 will be getting from this equation. Therefore, since the modulating or the reference signal has a square shape, this PWM technique is also called square wave inverter. Because here modulating or the reference signal, this is called modulating signal. Reference signal is also called as a modulating signal. We are modulating this. Of course, the magnitude of the square wave is modulated into the pulse width. It's actually pulse width modulation, in which as the magnitude of this modulating this reference signal changes, the pulse width is changing. That's why it's called pulse width modulation. And since this magnitude of reference signal has a square wave shape, it is called square wave PWM. next presentation will be the sine PWM, in which the reference signal is taken as a sine signal. That is why here, since we are using a square wave as the modulating or reference signal, this particular modulation technique is called square wave PWM inverter. Now continuing the multiple pulse modulation, square wave PWM, and here we are seeing the number of pulses per half cycle. Therefore, the number of pulses per half cycle of the inverter output voltage is equal to, in this case, as we are seeing, this is equal to Fc by F0. That's equal to, there are 6. This is 6, therefore 6 by 2. That is why the number of pulses per half cycle is equal to 3. Now here the RMS value of the output voltage. What is the RMS value of this output voltage? RMS value of this output voltage can be calculated as square root of 2p by pi. P is the number of pulses per half cycle. We are taking only this per half cycle, 2p by 2 pi, and we are taking this one, that is, here the limits are pi by 2 pi minus delta by 2. This here we are taking pi by 2p minus delta by 2 and plus delta by 2, and then that is, there are such 2p pulses are there. That is why we are multiplying with that one. 2p pulses are there. I mean here total 2p pulses, if you take total 2p pulses, and that is distributed over 0 to 2 pi. Therefore that is 2p in square root of 2p by 2 pi integral pi by 2 pi. This is pi by 2p minus delta by 2, pi by 2p plus delta by 2. These are the limits, v squared d omega t. If you integrate and dividing by this, I mean 2p by 2 pi, if you multiply that one and take the square root, we'll be getting v into root of p delta by pi. Therefore this is the RMS value of this voltage. Therefore, in order to change the RMS value of the inverter output voltage, you can change that delta, you can change. This pulse width can be changed so that the RMS value of this can be changed. The delta can be changed by controlling or magnitude of this reference voltage. By rising or lowering this one, the pulse width can be changed, or thereby delta can, changing the delta, you can change the RMS value of the inverter output voltage. Therefore, for example, in this case, when delta equal to 20 degree, that is if the pulse width equal to 20 degree, or it is in radians, pi by 9 radians, RMS voltage, that is RMS value of this voltage can be calculated v into root of here 3 into pi, in this case 3 into pi divided by pi by 8, or v by root 3. Therefore, the RMS value of this output voltage can be changed by changing the this pulse width. Again, to change this pulse width, you have to rise or lower this, of course, reference signal. Therefore, that is the control method is pictorially here. We are comparing the triangular wave signal, that's a carrier signal, with the reference signal. The reference signal is a square wave, and that is compared. And as the reference signal is more than this one, we'll be controlling the corresponding switches. And if it is less, it is switched off. And if it is more, it will be switched on. Thereby, you can get the pulse width of this output can be changed. So that is used to trigger this signal. I mean this for the positive half cycle, S1 is permanently on, you are controlling the S2, and for the negative half cycle, S3 is permanently on, you are controlling S4, so that this pulse width can be controlled and the RMS value of the output voltage can be controlled or changed. And of course, the frequency of this output inverter output voltage is decided by the frequency of the reference signal or modulating signal. Therefore, by changing the frequency of the modulating signal, you can change the output fundamental frequency, and by changing the this width of this pulse, you can change the, of course, the RMS value of the signal can be changed. This is the pictorially represented how the multiple pulse modulation technique is working in the circuit. Here, it's same circuit have been shown here: S1, S2, S3, S4, D1, D2, D3, D4. This is the DC bus voltage, and here these are switching signal during positive half cycle. Entirely, that is the gate signal is given to S1, and we are controlling the switches to S2. When it is on, this will be getting a positive voltage from here, and when it is off, you're getting a 0 voltage. That is during the positive half cycle of the output, and during the negative half cycle of the output, S3 is made to on, that is gating signal is given to S3, that is this one, and we are controlling the S4. S4 signal is given, and that this is being generated by this method. These signals are generated by comparing the reference signal with a triangular signal, and as the reference signal magnitude is more than triangular signal, you are giving the switching pulse. That is the way in which is producing this gating signal. And during the negative half cycle, you are switching on this one, that is S3, and we are controlling this switches S4. As S4 is on, we will be getting, of course, negative voltage. And as the level of the reference voltage changes, you will be changing the pulse width so that the RMS value of the output voltage can be changed. And the frequency of this one can be changed by changing the frequency of course, the reference signal or modulating signal, which is a square wave. And the average value of the output voltage, or the RMS value of the output voltage, RMS value of the output voltage is already we calculated, which is equal to V into root of P delta divided by pi. By changing the delta, you can change the value of the V. The same time, you can change the P also, the number of pulses per half cycle that can be changed, whereby you can change the RMS value of the output voltage. Therefore, thus we are getting a variable magnitude of voltage as well as variable frequency.